Thermite process, Van Arkel method, both are most important topics for PYQs. Hello students, let us start reduction and refining of metals. See, last total 5 steps we are going to follow in this extraction process. First 3 steps, 1, 2, 3 we studied in previous video. If not watched, watch previous video, come to this video. Fourth step continuation from previous video. Reduction of metal oxide into metal. Smelting. The process of heating ore along with reducing agent is known as smelting. Metal oxide heated along with reducing agent convert into metal. Reduction with carbon. So number of reactions with respect to different reducing agents. Here carbon is reducing agent. So same under fourth step. First reduction with carbon. Carbon is acting as reducing agent, reducing zinc oxide into zinc. Coke is not used for reduction of S block oxides and Al2O3 as it forms metal carbides. So this coke carbon cannot be used to reduce S block oxide and Al2O3 as it reacts and form metal carbides like this aluminum carbide. So it is not preferred. Reduction with carbon monoxide. So carbon monoxide also used as reducing agent here. Reduction with hydrogen. Hydrogen used as reducing agent. Next, thermite process. Reduction with aluminum. Here aluminum is acting as reducing agent. Thermite process. Suitable for Mn3O4, Fe2O3, Cr2O3 such oxides. Like Mn3O4 giving Mn plus Al2O3 when reacted with Al heat is. Okay. Process is also referred as thermite process or you can say aluminothermic process. Goldschmidt aluminothermic process, other name. So here it is ignite mixture, one type of mixture, magnesium plus barium dioxide or barium peroxide, magnesium plus barium peroxide, referred as ignite mixture. Thermite mixture, iron plus Al2O3. Thermite mixture, iron plus Al2O3. So first, ignite mixture reaction occurs, more amount of heat energy released. Same heat energy used by other reaction this one. So heat energy utilized by this reaction Fe2O3 reduced by aluminum and giving iron plus Al2O3. So here it is molten state. Molten iron you will get used in joining railway tracks. Even this thermite process used in joining railway tracks by using molten iron obtained by this process. Okay. Next, reduction with other metals. Titanium tetrachloride, magnesium, Ti plus MgCl2, which is Kroll-Kolin process. Other metals like magnesium. So Kroll-Kolin process. Titanium tetrachloride plus Mg giving titanium plus MgCl2. Self reduction or auto reduction. All these are under reduction methods. Cu2O, PbO, HgO, these three oxides reduced by auto reduction. Auto reduction meaning self reduction. There is no external reducing agent. See here now. Cu2s reacting with O2, partial roasting occurs. What is roasting? Conversion of metal sulfide into metal oxide in presence of oxygen. Partial roasting, some amount of Cu2s convert into Cu2O. Right. Whatever leftover amount here, same I am using here, see. Some amount convert into Cu2O. Remaining amount here, we are using remaining amount plus Cu2O formed in the reaction. Cu2O formed in the reaction, leftover amount further reacts and gives Cu plus SO2. So here if you observe it, there is no external reducing agent, only the substance whatever present here leftover, it is acting as reducing agent here. So there is no external reducing agent. Whatever reactant present here, it is acting as reducing agent and proceeding favorable for the reaction. Okay, that's why it is self reduction, auto reduction. Why we are using self reduction? There is no addition of any external reducing agent. Only one of the reactants acting as reducing agent. So here you can see it is reducing agent in this case, which is reducing Cu2O. Electrolytic reduction, Downs process. Here electrolyte is molten NaCl plus CaCl2, anode is graphite, cathode is iron. Anode reaction, anion move towards anode, lose electron form Cl2 gas. At cathode, Na plus gain electron form Na. Downs process. Purification or refining. Liquation, when there is large difference in melting point of metal and impurities, we use liquation. Like tin, lead, zinc, antimony, bismuth, mercury, low melting point metals, you can purify by using liquation. So what we do, if we keep this powdered ore on any flat surface and heat it, low melting point metals flows down, whereas impurities stay there itself. Distillation, when there is a large difference in boiling point of metal and impurities. Melting point difference, liquation, boiling point difference, Distillation. Distillation method, zinc, cadmium, mercury, low boiling point metals. Same, on heating, low boiling point convert into vapor form, we can collect it separately. Zone refining, it is used for metal where high purity is required, like silicon, germanium, gallium, semiconductors. Where we need high purity metal, then we use zone refining. It is based on principle that impurities are more soluble in molten metal than solid state of metal. Impurities are more soluble in molten metal than solid state of metal. For example, see here. Here we are taking one metal rod. We can say impure metal rod where impurity is also present. So to this impure metal rod, we are connecting one moving heater. Moving heater. So what we are doing, moving heater, we are starting here. Actually, we can move this left and right. We can move this moving heater. We are starting from here, which is preheated moving heater. So after heating this moving heater, slowly, so the impurities present in metal rod dissolve. The impurities present in metal rod. So first of all, here this metal rod becomes molten state in the given container. It becomes molten state. So now, as we are moving heater from one end to other end, we are moving heater from one end to other end slowly. What happens as we are moving away from this particular metal rod, which is present in the container, thing that pure metal solidify, whereas impurities travel along with the moving heater, because moving heater here molten zone it is. So this moving heater carries impurities, because impurities soluble in molten metal than solid state. Here, as we are moving away from this one end, here metal becomes solid again. So along with the heater, impurities travel. After completion of process at one end, at one end, all the impurities settle. Again, we are bringing heater here from one end, again slowly moving other side. So what happens here? As we are moving away from one end, here again solid metal solidify. Then impurities travel along with heater. So as we are moving heater at one end, all impurities concentrate. If you repeat this process number of times, after completion of process at one end, all the impurities concentrate. Then finally you can cut this particular part, you can remove it, remaining is pure metal. So just we are washing impurities by heating it simply. We are washing impurities by using heater. We are moving heater from one end to other end, so that impurities we are bringing to one side. Besmerization or puddling process used for pig iron or raw iron. To remove volatile impurities, molten metal is placed in Bessemer converter and hot air is passed into a container. Whenever pig iron, if we take, hot air is passed, it is converted into steel. What is steel? Steel is iron with small amount of carbon. Plus vapors of impurities goes away. So when pig iron, that is molten iron, present in the container, if you pass hot air, it is converted into steel form, iron plus some carbon content, vapors of impurities goes out. This process is besmerization. Poling process used for purification of tin and copper. See, poling process, here we use green poles of wood. Fresh wood is dipped into molten iron. For example, if I think that here you take it molten SnO2. Molten SnO2 if I take. So SnO2 molten form, CH4 from green poles. See, we are taking one container where SnO2, molten SnO2 into this green poles of wood. We are stirring the molten solution with the green poles of wood. We are taking green poles of wood and stirring the molten solution. These wooden poles generate methane gas. Green poles of wood generate methane gas. So methane gas reduce SnO2 to Sn. Here you will get pure metal. Impurities like CO2, H2O goes out. It was old method, ancient method, previously used to purify by using this method. SnO2 we are melting in particular container. Into this container, we are introducing green wooden poles, freshly cut branch of tree, stirring it. Due to high temperature, these green poles release CH4 gas. CH4 gas reduce SnO2 into SnCO2 H2. Okay. Vapor phase refining, two methods, Van Arkel method, Mons process. Van Arkel method used for titanium as well as zirconium. These examples very important. Used for nickel. Titanium along with impurities heated with iodine. Titanium along with impurities heated with iodine 250 degrees Celsius gives titanium tetraiodide volatile. titanium tetraiodide volatile, that is gas. Vapor of the compound titanium tetraiodide. And then at 1400 degrees Celsius, on heating at 1400 degrees Celsius, titanium solid plus 2I2. Titanium solid plus 2I2. So here first we are converting titanium into soluble form, that is volatile form. On heating this volatile compound, iodine goes away, giving only titanium pure. So iodine goes away, we are getting pure titanium, that is overall. So here titanium tetraiodide volatile compound, on heating it we are getting pure titanium as elimination of I2. Impurities left in container itself. Next, used for nickel, same process. Nickel heated along with carbon monoxide along with impurities, because nickel along with impurities present, we are using carbon monoxide, here iodine. So now at 50 degrees Celsius if we heat, it forms again nickel tetracarbonyl volatile compound, gaseous compound, it is also gaseous. On heating further, CO gas goes out, leaving pure nickel to us. At the same time, impurities present in container itself. Here also impurities left in the container. Just we are converting iodine into vapor form, getting titanium into vapor form, getting pure titanium. Here nickel into vapor form, getting pure nickel. So overall impurities left in the container. Important examples you have to remember, and reactions you have to remember. Cupellation used to purify silver by separating Pb impurity present along with it. Cupel meaning here container, cupel shaped container. So used to purify silver by separating Pb impurity. What we do in the container where Pb and silver present, blast of hot air is introduced, where hot air react with Pb, convert into PbO, oxidized and blown away along with air. So Pb removed. Silver is purified. Electrolytic refining in aqueous solution. Electrolytic refining in aqueous solution used for copper, silver, nickel, etc. Remember, more reactive metals like potassium, sodium, calcium, magnesium, aluminum cannot be purified by this process. Cannot be purified by this process because in this electrolytic process, H2, that is hydrogen, that is more reactive, having more SRP value. So hydrogen goes reaction at cathode instead of anode. So here these more reactive metals we should not use for the electrolytic refining, because the more reactive hydrogen in terms of SRP undergoes reaction. Impure copper is anode, pure copper is cathode. Electrolyte aqueous copper sulfate. Electrolyte aqueous copper sulfate. Electrolyte aqueous copper sulfate, remember reactions at anode, copper lose 2 electrons and convert into Cu plus 2. Cathode, Cu plus 2 gain 2 electrons and convert into copper. So what's happening here, you observe it. Here copper lose 2 electrons and convert into Cu plus 2, same Cu plus 2 again goes and deposit on the cathode. After completion of process, we get thick cathode, that is pure copper at cathode. Anode becomes thin after completion of process. That's what we showed reaction. You see copper losing 2 electrons and forming Cu plus 2. A Cu plus 2 formed here. And then Cu plus 2 move to cathode, gain 2 electrons and form copper. So pure copper you will get after completion of process. If any insoluble impurities, like even some trace quantity of silver, gold also present in it, which is called as anode mud at the bottom of the tank. Parting process, molten state of gold plus silver impurity. So molten state of gold plus silver, here impurity present. We are using Cl2 gas, Cl2 precipitize Ag, forms AgCl. So AgCl precipitate formed as a layer on the surface of molten metal, we can separate it and then we will get gold. Parks process, desilverization of lead, used to remove silver from argentiferous lead. Argentiferous lead where lead plus silver impurity is present. So here we are going to remove Ag. Silver is more soluble in molten zinc than molten lead. Silver is more soluble in molten zinc than molten lead. So what we are doing, to this container where Pb plus Ag, we are converting into molten state, 1% zinc we are adding. So silver form zinc alloy. Silver form zinc plus silver alloy is formed and floats on the surface of molten Pb. So we remove this alloy. So molten Pb, that is pure form. Okay. So silver forming alloy with zinc. So this particular layer we can remove it so that we will get pure lead. This is JEE Main's 2021 question here. First you read question. The metal that can be purified economically by fractional distillation method is. See, distillation method mainly preferred for low boiling point metals. Just now we discussed distillation. So low boiling point metal, that is zinc is correct. Above already we discussed, once you refer it. Next question. Question C, the Goldsmith aluminothermite process, which of the following reducing agent is used? So in reducing agent is aluminium in above method. Clear? See, thermite process and Van Arkel method, Mons process, very important questions. Number of times they asked in PYQs. Okay. I hope all the questions clear to everyone. For more updates, follow the channel. Thank you. Thank you everyone.